In this second organic chemistry video, I'm going to talk about the different families of organic molecules you need to know about. I'm going to talk about alkanes and alkenes in a bit more detail for the first video. Alcohols, carboxylic acids and esters. I'm going to remind you that these are all what we call homologous series. So homologous series, you're expected to know that term and understand that that is a series or a family of molecules with the same general formula. So for example, the general formula of alkanes is CnH2n plus 2. They therefore have similar properties and similar reactivities. And you also need to know that within a family they differ by CH2. So if you go from methane to ethane, you gain a CH2. Go from ethane to propane, you gain CH2. You're expected to know the prefixes for organic molecules: meth, eth, prop, and bute. Monkeys eat peanut butter, and that's 1 carbon, 2 carbons, 3 carbons, 4. And I drew these out in the previous video, so I'm not going to draw them again now. Methane, ethane, propane, butane for alcohol, for alkanes. For ethene, it would be alkene, propene, and butene. Got to make sure you can draw all of those molecules absolutely fine, making sure that always carbon has 4 bonds and hydrogen has 1 bond. Alkenes have got the general formula CnH2n. Alkenes are more reactive than alkanes because they've got that double bond. I'm going to draw ethene just to remind you what it looks like. And propene, showing you that it also has a double bond, just 1 double bond between 2 of the carbons. And be careful when drawing propene, because yes, it's got a double bond, which means you've lost a hydrogen from here if you compare it to butane, and lost a hydrogen here if you were to compare it to butane. Well, as I said a moment ago, as you go through the homologous series, you gain CH2 each time. So you can see that up to this point, if you go from right to left, if you like, that bit's the same and that bit's the same. You've gained 1 carbon and 2 hydrogens. You gain CH2 each time. It's C2 H4 to C3 H6. You've gained 1 carbon and 2 hydrogens, right? So the focus of this talk is mostly going to be about the reactions of the different families of organic molecules. The first thing I'm going to talk about is just hydrocarbons in general. So this applies to alkanes and alkenes. So it's going to put CnH X, okay, or C. I could put CXHY. So any hydrocarbons this applies to could be alkanes or alkenes, or indeed something called alkynes, which we don't study at GCSE. Now you all know hopefully that they burn in oxygen. If you've got an excess of oxygen, you get carbon dioxide and water, and you'd be expected to balance an equation like that. You can also get incomplete combustion, which is when there's insufficient oxygen, and then you'll still get water, but you could get carbon or soot as a product. You could get carbon monoxide, which is partial oxidation of the carbon of the hydrocarbon, and you could still get some carbon dioxide as well. So you need to know about complete and incomplete combustion. Incomplete combustion tends to happen more with alkenes. So alkenes tend to give you smokier flames. The smoky flame is partly due to the carbon soot given off. It might also be some unburned hydrocarbon as well, but so mainly it's the soot given off that's giving you the smoky flames. Okay. So alkenes are more likely to undergo incomplete combustion, give you smokier flames. That's the key learning point there. Alkenes are what we call unsaturated. Unsaturated means they've got a double bond, really. It means that there's room to put more hydrogens on there. And the equivalent alkane has got 2 more hydrogens, and the alkanes are saturated. So unsaturated for alkenes and saturated for alkanes. Right, so some reactions then. So I'm going to just focus on alkenes for the time being. I'm going to use ethene as my example. And I would definitely have flashcards on this that also have maybe a revision map with maybe all of the reactions of ethene or an alkene shown. So the first couple I've already told you about. We've got complete combustion with excess oxygen, can give you carbon dioxide and water, or you can get incomplete combustion with limited oxygen, will give you carbon monoxide and possibly carbon dioxide and water. You get all of those things. The other reaction we've talked about so far is the reaction with bromine water, which is the test for alkenes. And you can get more than one product, but the one that the GCSE expect you to know is that when you shake bromine, which is orange, with if you shake bromine water with an alkene, bromine water is orange, you'll go from orange to colourless. So orange to colourless. What you get there is the formation of this, and this is the first example of an addition reaction. You're expected to know that alkenes undergo addition reactions very readily. They're quite reactive. They're reactive because of the double bond. I'm going to highlight to you using a red pen what's happened here. So this CH2 here that's ended up in the molecule of the product was this CH2, and the one on the right hand side, which I'll colour with green, this CH2, if I can get the pen to work, this CH2 was this CH2. So the bromine that's added to it, the bromine molecule, which you could have drawn as Br, line Br, because they're bonded with a single bond. The bromine on the left ends up on this carbon, the bromine on the right ends up on this carbon. They add to it, so it's two molecules become one. That's what an addition reaction means. And you're expected to know that term. So addition reaction, if you think about it, two becomes one. Remember that song. Okay. And lots of the reactions of alkenes are also addition reactions. So apart from the reaction with halogens, they can also react in a similar way with hydrogen in the presence of a catalyst. Now this reaction doesn't require a catalyst. As you know, you just shake it and it goes really quickly. With hydrogen, you can add a little catalyst in there. So the reaction with hydrogen is exactly the same as the reaction with bromine, except we're using H2 instead of Br2. So you get the same sort of thing happening, addition reaction, and we end up with the new hydrogen has been added across that double bond again, making this time the alkane. Again, it's an addition reaction. The hydrogen H2 is added across the double bond. Now, when you just worth going back to this, when you draw this, the hydrogen bromine on the left hand side here, the hydrogen bromine and the other hydrogen, doesn't matter which way around you draw them, as long as you've got one bromine attached to this carbon somewhere and one bromine attached to this carbon somewhere. The Br could have been down here or up here or here, it doesn't matter. Another reaction is the reaction with, technically it's water, but it only works if water is steam. So water's a gas, and again you need a catalyst for that, otherwise you have to get it very, very hot. If you do that reaction, this is slightly harder to get your head around, but if you think of water as being like that, water is a hydrogen attached to OH, if you like, then you can see that just like the hydrogen before, the H will add to one of the carbons, and the oxygen, the OH, will add to the other carbon. What you get then is something called an alcohol. That was the hydrogen that was this hydrogen here, and then the OH from the water adds to the other one. So this is what we call an alcohol. Oops, alcohol. This specific alcohol has got two carbons, so we call it F. F for two carbons, and because it's got no double bonds, ol because it's an alcohol. So F and ol, so three parts to the name. You can also write that CH3, CH2, OH, showing that functional group there. And sometimes you have to put circles around functional groups. The functional group at the end there, so CH2OH, This is the process, one of the ways that ethanol is made. I'll come back to ethanol a bit later on. You need to be able to compare and contrast two ways of making ethanol, because ethanol's got all sorts of uses. This is one of them, and it's a very efficient, high yielding, high atom economy, because it's only one product route to making them. The end of the things I mentioned briefly is that you can do something called addition polymerization, which I'm going to come to in the next video. Addition polymerization. So that might go onto your notes when you finish making your own notes, or revision slides or whatever. And the other thing that I should say is that this reaction we've covered already, this addition of bromine to the alkene. It could be any of the halogens, so it could be Cl2 adding to it, so Cl there and Cl there. So it works as well with Cl2 or I2. And what you get there is, this is what we call a di, because there's two of them, bromo, because it's got bromine, ethane, dibromoethane, specifically 2-dibromoethane, because one's on the first carbon and one's on the second carbon, but dibromoethane is what we form when we add bromine across it. Dichloroethane if you add a chlorine to it, and diiodoethane if we add iodine to it. Okie dokie. This is a good time to identify or show you that a good way of some good notes here are in your revision guides, but also the physics and maths tutor notes are pretty good, which I'm using just to remind me of some things you do and don't need to know while I'm talking you through it. So I'd recommend you use that, and the questions that come with that are excellent too. Right, so I'm going to talk about another functional group now, or another family, another homologous series, the alcohols. We've already talked about the way we make alcohols, which I mentioned briefly again, via that addition reaction between ethene, C2H4, and steam, which is a gas in the presence of a catalyst, to give you ethanol. Oops, that's a pretty ugly drawing. That's just an H on the end of a line. And there's ethanol for you. This time I've drawn the OH in a different position. It doesn't matter, it's exactly the same thing as long as you've got an OH hanging off that carbon. You can have other length alcohols, so you can have methanol with one carbon, or propanol or butanol or whatever with different numbers of carbons. But I'm just sticking with ethanol because you're expected to know how ethanol is made. You'll also know that ethanol can be made via fermentation. You'd have covered this in biology. So glucose or sugar can be used to produce ethanol via a process called fermentation. And that's done in the presence of an enzyme. And without oxygen, and I spelled that wrong, aerobic. So it's without oxygen, undergoes fermentation, and you end up getting ethanol produced. So glucose is C6H12O6, you know from biology, and we end up with two ethanol molecules, C2H5, that's the CH3CH2, C2H5OH, plus 2 CO2, and this is this production of carbon dioxide during fermentation that causes lots of alcoholic drinks to be fizzy, like champagne, of course, is fizzy. It's fizzy because of carbon dioxide dissolved in it, which is a hangover from the fermentation process. Fermentation is a biological process done with an enzyme, and that enzyme is within the yeast, and therefore reaction has to be kept at the temperature about 35 degrees C. Too high and the enzyme in the yeast will denature, the reaction doesn't proceed, and too low, the reaction is simply too slow. Okay, so faster rate of reaction, the fastest rate of reaction you could possibly do at the highest temperature without denaturing the yeast. Now this reaction works fine. You can do it at relatively low temperatures compared to the steam reaction I've mentioned up here. So that's an advantage. It is cheaper to do and easier to do, and you need different feedstocks that you can get and that you can grow. So glucose, of course, you can get from things like sugar beet, sugar cane. Ethene you have to get from cracking, from crude oil. So finite resource and renewable resource. The disadvantage of this method, though, is that the maximum yield you can get is something like 15%. So you can't get a high concentration of ethanol production. So you have to do subsequent steps of distillation if you wanted pure ethanol. There are some uses of ethanol which you need to be aware of. So you can use them as a fuel, and they burn really well. I'll talk about the reaction of burning of ethanol and the alcohol shortly. But you can make they can be used as a fuel. You can use them in biodiesel, for example, as a and it's biodiesel because you can make it from a renewable resource, the glucose. You can use it in antifreeze. You can make it, of course, to be useful as an alcoholic drink, solvents, all of that kind of stuff which has been mentioned. But you need to know uses. So I'm just going to write uses down there. Fuel, solvent, two big ones. If you're going to remember two, remember those two. Okay. And I think cover that. Right. So I'd encourage you now to do a revision sort of notes for reactions of ethanols or alcohols. I'm going to use ethanol as my example. I'm going to draw the OH on the right hand side. OH, it's always the oxygen makes two bonds. Oxygen's bonded to the carbon and the hydrogen. Okay, and that's the functional group. The first thing I would do is to identify the ways of making them already, which I've already covered. I'm not going to do that again. You can make them on your revision sheet from ethene or from glucose, and then some reactions of them. Now, there's just a few things you just expected to know. First thing, just like any organic molecule, you can burn them in air, in oxygen, and what you get is the hydrogens get fully oxidized to water, and the carbons get fully oxidized to carbon dioxide. Just complete combustion, just like hydrocarbons. These are more likely to undergo complete combustion because you've already got one of the oxygens you need as part of the molecule. So they tend to get quite a blue flame, quite hot flame, as some of you seen brandy being set fire to on a Christmas cake or something. You know, it's a very blue flame. It's a sign that it's complete combustion going on there. They give off plenty of heat, so they're quite useful. Okay, so reactions they will undergo then. The first one is a bit of a random one. They want you to know, which is if you chuck in sodium, they behave in a similar way to when you react sodium with water. Now, if you look up, I'm going to draw it up here. If I draw water looking like a bit like my alcohol, so there's water up here, there's my alcohol here. If you chuck sodium into water, you might remember, when you've done that, you generate hydrogen and you generate sodium hydroxide. I haven't balanced that equation. It would be two of those, and two of those. But what you expected to know, you produce hydrogen, and you expected to know that the Na will end up hanging off the rest of the molecule. So let's see what's going on here. So we know we're making hydrogen, and the other hydrogen, if you like, has been replaced with the sodium, and that's what happens to this one. So this hydrogen becomes the H2 and is replaced with an Na. There are uses for that, but they don't want you to know what they are, which is a bit unnecessary, a bit strange. There we go. That's what you get produced. You get sodium ethoxide produced. That's a minus charge, that's a plus charge, that's an ionic bond there. That's called sodium ethoxide. The only other one you really need to know then is that if you oxidize ethanol, you have to use specific conditions to oxidize. But one of the ways you can oxidize ethanol is actually to allow wine to sit open for a few days, and it will oxidize. And when it oxidizes, or you oxidize it with specialist oxidizing agents that we represent with the letter O in square brackets, what we end up is something called ethanoic acid. And that's the stuff you find in vinegar, which is why wine, if you leave it open for a few days, tastes kind of acidy. It's ethanoic acid, or weak acid, that you learned about in the acids topic. It's worth noting when you do that, to balance this equation, these hydrogens have to go somewhere. What happens to them those hydrogens end up in a water molecule. So to make this balanced, we've got 1, 2, 3 oxygens in our products and only one there. So we have 2 of those. One of those oxygens ends up in the molecule there, and the other of them ends up in the water here with the 2 hydrogens. Okay, that's what's going on. So that's oxidation of alcohols to give carboxylic acid, specifically ethanoic acid from ethanol. That's about it for alcohols, except you're expected to know also that they dissolve in water and are neutral. So soluble, which we know because we know that ethanol dissolves in water, because that's what we have in alcoholic drinks. And they have a pH of 7, not acid or alkaline at all. We know already about ethanoic acid, we just talked about it. That's that carboxylic acid. It's a weak acid, and it's worth going back at some point over your acids topic, making sure you know about weak acids and how they behave. They react just like strong acids, only they do it more slowly. They do all the kind of same things as acids do. And it's worth highlighting that you can have a full family of these. You've got ethanoic acid I've drawn for you. You can have methanoic, propanoic, butanoic acid, and that corresponds to the number of carbons, including the one that's part of this functional group here. You should also know you can write the formula of these, CH3COOH. The CH3 there, COOH. You can write them like that. So the reactions are, again, you knew this from the acids topic, but if you chuck them into something like a reactive metal, like magnesium, they'll react very slowly, but they'll react to give a salt. And sodium, they'll react quite a bit faster to give a salt. But the ones that they really seem to want you to know, so I'm not going to dwell on this too much. I sped that up there by pausing it. But you've got the hydrogen comes off, just like with the alcohol, the hydrogen comes off to give you the what we call the ethanoate ion, which is what I've drawn in the bracket there. And 2 of those are required per magnesium, because magnesium is in group 2 and has a 2+ ion. Okay, so you get this kind of thing going on. What's much more likely that you're expected to know is they react with carbonates. I'm going to use this to show that. So metal carbonates or metal hydrogen carbonate. So for example, what should I use? I'll use sodium carbonate. It could be calcium carbonate or sodium carbonate. And they react like any carbonate plus acid to give salt plus water plus carbon dioxide. And you know, if you're not sure, at least guess, because you often get marks one at a time for these things. So the salt is the same thing we've drawn. I'm going to show you a different way of drawing it. So just lost the hydrogen, replaced it with the sodium from the sodium carbonate. You get carbon dioxide and you get water. That again is not balanced. We need 2 of these, don't we? If we've got 2 of those, we have to have 2 of these because we've got 2 sodiums there, so 2 sodiums there, and therefore we need 2 ethanoic acids. And then I think that's balanced. I'm just going to check. Yeah, of course it's balanced. So you might get marked for working out that it's carbon dioxide and water. You might get an additional mark for working out that it's sodium ethoxide. But the idea is the hydrogen that's interesting, sometimes called the interesting hydrogen, if you like, is that one there. They do of course dissolve in water and have pH of less than 7 because they're acids, which is why they're acids. And the last thing I'm going to show you is the reaction between what we've just learned about, ethanoic acid and ethanol. So make sure you can draw these, very commonly asked. So if there's ethanoic acid, ethanol, I'm going to flip it around from the way we've drawn it before. There's ethanol, just turned it around just to point the functional groups towards each other because they react with each other to form the product. The product is an ester, and what's happened there, this is a condensation reaction. Condensation reactions are reactions which produce small molecules, typically water. In this case it is water. So if you look at the 2 molecules above, the ethanoic acid and the ethanol, the OH of one of them and the H of the other get together and hang out and become water. Now it is this way round, it is this OH and this H that join together. But if you get it wrong in the exam, you're not expected to know that. You get the same product if you lose this OH and this H, you get the same thing. And what must happen is carbon always makes 4 bonds, and this OH is gone, so this carbon has to be bonded to something new. And this oxygen always makes 2 bonds, it's lost a hydrogen, so it has to be bonded to something new. So they, that's my green pen gone, so never mind. They end up joining together to make the product. So I'm just going to draw everything and be really careful to copy as much as I can. The CH3 is here on the left, then the C double bonded to O, and that carbon, which is that carbon, is now bonded to this oxygen. There it is. And then you've just got to draw the CH2 and the CH3. So that stuff is called ethyl ethanoate. And it's the only ester, it's the only ester you have to know the name of, ethyl ethanoate, because both halves have got 2 carbons. The bit that I'm showing now is called the ethanoate because it came from ethanoic acid, and the ethyl bit is because it's a short chain which has 2 carbons, and that stuff's called water. If you're asked to highlight what the ester functional group is with a ring, put a ring around that section there. You need it to be carbon that the oxygen's bonded to, but that's the bit that's the ester, at least according to the exam board's mark schemes. Okay, this is the only ester you need to know the name of. This reaction only happens in the presence of a catalyst, which is an acid. Okay. I think that's all the reactions you need to know from what I remember.